ポケモンゲットだぜ。
The algorithm team has used the right wall hugging method to conduct the exploration phase. If wall hugging has been completed but the phase is not fully explored, the robot will conduct a second round of exploration with the fastest path possible. The robot will advance multiple cells if possible to speed up the exploration. We are also responsible for developing a simulator to demonstrate the complete exploration of the unknown maze as well as the fastest path. The simulator can work independently without any help from other teams.
For the fastest path, we have chosen A-star algorithm that returns us the less expensive path with the knowledge of Manhattan distance heuristics. The A-star algorithm begins at the start node and considers all adjacent cells. Once the list of adjacent cells has been populated, it filters out those which are inaccessible. It then picks the cell with the lowest cost recursively until the shortest path has been found to the goal node. After the first two leaderboards, we have decided to come up with a few optimizations to improve our results. We implement the algorithm part on Android platform to reduce overhead implementation. Apart from that, a diagonal fastest path algorithm is implemented to reduce the number of turns that the robot needs to take.
This is where it all first began for our Android development team. A robust Bluetooth connection service is paramount moving onward to future developments. So, our Android team actually built a steadfast Bluetooth communication service from the ground up. This allows us to separate the concerns of Bluetooth and the maze, allowing the consistent to be persistent in the background. This ensures that devices are connected even in the event that a user accidentally switches out or closes the application. On top of that, audio cues were also incorporated into the application to inform users of key events such as reaching the waypoint or the end zone.
Bearing in mind that user experience is quintessential in Android app development, the Android team went all out in creating an aesthetically pleasing 3D Pokemon themed GUI. This includes building a Pokemon cave related game as well as modeling the robot with a 3-dimensional edge sprite. Moving on, a rectangular pad that's implemented on-site listener serves as an alternate way to control the robot on top of just buttons. If a user stride exceeds the minimum threshold velocity, the corresponding move command will be called.
The R5 team uses Python packages to implement all the multi-threading processes between all the devices. With the integration of the algorithm into Android, data passing is done only between the Arduino and Android device. As a result, only 6 threads are required, with 2 each for reading and writing to Arduino and Android device, and 2 for capturing and processing of images.
With the addition of the image recognition leaderboard, the RPI is also required to detect arrows placed in the arena and accurately identify the direction of the arrow and also the location where the arrow was detected. This is done so by capturing images of the arrow using the onboard Pi camera and template matching techniques with the broken CD packages.
Total of 5 infrared sensors on the robot, 3 short range facing the front, 1 short range facing the right, and 1 long range facing the left. Sensors are mounted vertically below the acrylic board to reduce the interference effect of the signal received, to ensure the infra reflect off the block and not the arrow image. As the sensors are the eyes of the robot, we spend most of the time adjusting the obstacle detection threshold range. For example, an obstacle is within 1 grid away from the robot. The sensor reads about 125mm and is within the threshold range to return value 1 to L1.
Due to the motor's unequal speed, we use PID controller to balance the speed equally. This enables the robot to move in a straight line, consistently and turn accurately. The rotary encoder enables us to measure the number of times it took to rotate the wheel for a certain distance on the arena. For example, a 4-grid movement through the maze, it takes about 1,200 times to complete the distance, and a diagonal 45 degrees turn requires only about 200 times.
As the front-facing left and right sensors are equal distance, we use the concept of balancing their values as this makes the robot perpendicular to the front-facing obstacle, aligning it within 3 by 3 and 5 cm away from obstacles surrounding it.
Leaderboard-wise, our team was slow off the blocks. In the initial 3 leaderboards, the robot failed to calibrate properly, went off-grid during exploration, and sensed the phantom block which caused the robot to shut down. But like all fairy tale endings and with a lot of hard work and perseverance, we managed to turn things around and eventually qualified for the last leaderboard with an impressive time of 2 minutes and